Hi everyone, welcome to Potato Chemistry. In this video, we will learn how to write chemical equations. By the end of this video, you should be able to understand the differences between a word and a symbol equation, more simply known as a chemical equation. You should also be able to name the different parts of a chemical equation. Next, you should also be able to state the differences between two types of numbers in a chemical equation. One is called a coefficient and the other is called a subscript. Finally, you should be able to balance chemical equations. Let's start off with the differences between word equations and symbol equations. And to do this, we'll use the neutralization reaction between sodium hydroxide and hydrochloric acid as an example. Now, these are two ways to represent in writing a real chemical reaction. You can pause the video for a minute and jot down on a piece of paper as many differences as you can find between these two types of equations. One of the most obvious differences between the two of them is that the word equation displays the chemicals by their English names, whereas the symbol equation, or more simply the chemical equation, display the chemicals as their chemical formula. Now this brings us to our second point. Word equation contains no information on the chemical formula of the reactants or the products, whereas symbol equations do contain such information. Next, word equations also do not contain information regarding the ratio of reactants to products. You can probably guess this because word equations are written in words, whereas ratios are numbers, right? And there are no numbers anywhere in a word equation, so obviously it cannot contain such information. Whereas in a symbol equation, this information is displayed as coefficients. We'll see in later slides what exactly coefficients are, but for now, coefficients are these numbers on the left-hand side of every term. If it's not specified, it simply means a coefficient of 1. In this example, the coefficients tells us that in a complete neutralization reaction between these two chemicals, 2 molecules of sodium hydroxide reacts with 2 molecules of hydrochloric acid to produce 2 molecules of sodium chloride and 1 molecule of water. Knowledge of the ratio of reactants and products is very important in optimizing chemical reactions. Finally, word equations also do not contain information regarding the state of matter of the reactants or the products, whereas in symbol equations, this information is displayed in brackets. So bracket AQ means that the substance is dissolved in water, whereas L means that the substance is a liquid. So here we can see that sodium hydroxide is used as a solution, hydrochloric acid is used as a solution, and they both react to produce sodium chloride, which is also a solution, and it also produces liquid water. Next, let's understand the different parts of a chemical equation. The chemicals that the arrow is pointing from are called the reactants, whereas the chemicals that the arrows are pointing towards are called the products. Reactants are not necessarily always on the left and products are not necessarily always on the right. This is especially true in reversible reactions. For the reverse reaction, the reactants are on the right, whereas the products are on the left. To determine from a chemical equation which chemical is the reactant and which one is the product, we have to look at their position relative to the arrow. Next, this big number that lies on the left-hand side of some of the terms are called coefficients. And the concept of coefficient here is similar to the concept of coefficient in algebra. Coefficients are multiples of the term that comes after it. In algebra, if it's 2x, what it means is that there is 2 of x. 4x means that there is 4 of x. Similarly, 2H2 means that there is 2 of H2. But what does it mean to be H2 and how does it differ from just H? To understand this, we have to understand what is a subscript. This small number on the bottom right of a chemical symbol is called the subscript. A subscript indicates the number of atoms of a certain element that is present in a substance. H subscript 2 means that hydrogen exists not as a single atom, but as a hydrogen molecule, which consists of 2 hydrogen atoms, hence H2. But you might notice that there are several terms where the coefficients or the subscripts are not specified. For example, there is no coefficient specified for O2, and there is no subscript specified for the oxygen in H2O. Now, whenever coefficients and subscripts are not specified, they are assumed to carry the integer value of 1. Let's look at the differences between coefficients and subscripts in a little more detail. As mentioned before, coefficients are multiples of the term that comes after it. 2x means that there is 2 of x, 2xy means that there is 2 of xy, 2H2O means that there is 2 of H2O. A very important point to remember is that coefficients do not change the chemical properties of a substance. 1H2O simply means that there is 1 molecule of water. So if you have 2H2O, all it means is that you have 2 molecules of water. Right? Chemically, they're the same. You just have twice as many. In contrast, subscript indicates how many atoms are there in a molecule. If the subscript is 1, it means that there is only 1 atom. So in this case, it means that there is only 1 atom of X. If it's X subscript 2, then it means that it's a molecule consisting of 2 atoms of X. Unlike coefficients, which do not change the chemical properties of the substance, subscripts will change the chemical properties of a substance. And we will illustrate this with an example. If we start off with 1H2O, it means 1 molecule of water. Notice that the coefficient is not specified if it carries the value of 1. If we increase the coefficient to 2, all it means is that we now have twice as many water molecules, but chemically, they are still identical. However, if you increase the subscript of oxygen, for example, to H2O2, now we no longer have a water molecule. Now, this is a molecule of hydrogen peroxide, which is a type of bleach. Now, bleach and water are chemically very different. In fact, there is a well-known chemistry joke that revolves around the differences between hydrogen peroxide and water. If you have never heard of this joke, just Google 2 chemists walks into a bar and you should be able to find it. Next, let's talk about the state symbols. In this example, hydrogen reacts as gases, oxygen reacts as gases, and the water that is produced is also produced as gases. So, what are the rules in writing state symbols? Now, state symbols usually refer to the state of matter of the reactants and the products during the chemical reaction. In this example, this is a highly exothermic combustion reaction, so the water that is produced will come out as steam rather than liquid water. To indicate solid state, we use bracket lowercase s, liquid state bracket lowercase l, gas state bracket lowercase g. If we're talking about a substance that is dissolved in water, then it's bracket lowercase aq. It's called aqueous, and it means that the substance is dissolved in water. One of the key characteristics of a chemical equation or a symbol equation is the use of chemical formulae. In this video, we're not going to discuss how to write the chemical formulas for compounds because that would be a video in and of itself. However, I would like to address how do we write the formulas of elements. For example, if you refer to a periodic table, you can see that the formulas for hydrogen and oxygen are H and O respectively. So why is it when we're writing it in this equation, they become H2 and O2? What are the rules here? In general, we're writing the formulas for the elements as they would exist under standard state conditions. This would be 25 degrees Celsius and 1 atmosphere of pressure. 1 atmosphere is the pressure at sea level. Under these conditions, halogens usually exist as diatomic molecules. Di means 2, so diatomic molecules means molecules that contains 2 atoms. So the general formula for halogens would be X2. In writing chemical equations, the element fluorine would typically be written as F2, chlorine as Cl2, bromine as Br2, iodine as I2. Oxygen, as we have seen already, also exists as a diatomic molecule, O2, nitrogen as N2, and hydrogen as H2. Now, for an introductory level of chemistry, we can assume that all other elements exist as single atoms. X, where X is the element symbol. For example, aluminium is just Al, no Al2 or Al3. Same goes for iron, zinc, helium, argon, and so on. This assumption would not be true at higher levels of chemistry, but it should suffice for an introductory level. Finally, if you have ever seen a chemical equation before, you would realize that the coefficients and the subscripts of every term in most equations are not the same. For example, sodium has a coefficient of 2, whereas chlorine doesn't. Chlorine has a subscript of 2, whereas sodium and sodium chloride does not. So what are the rules here? What is the purpose of using these coefficients and subscripts? We write chemical equations in order to represent in writing real-life chemical reactions. And in real-life chemical reactions, mass is always conserved. What this means is that atoms do not disappear or change in terms of the type of element. The products of a chemical reaction must contain exactly as many atoms of each element as the reactants. In actual chemical reactions, mass is naturally conserved. However, when we are representing them in writing, mass isn't conserved because we're not actually performing the chemical reaction. We're just putting ink on paper. So in order to accurately represent a certain chemical reaction, the conservation of mass has to be done also in writing. The process of conserving mass when we are writing chemical equations is known as balancing the chemical equation. In the example above, you can see that there are two elements that are present here, sodium and chlorine, and this should be true for both sides of the equation. Elements cannot change over the course of a chemical reaction. That would be alchemy, which is a pseudoscience. Now, let's use our knowledge of subscripts and coefficients to count the number of sodium and chlorine. So we have a coefficient of 2 for sodium. That tells us we have 2 sodium atoms on the side of the reactants. And we have 2 NaCl. That means we have 2 sodium on the side of the products. For chlorine, we have C subscript 2. So this is a molecule of chlorine consisting of 2 atoms. Whereas on the side of the products, we have 2 NaCl. So we also have 2 chlorine atoms. So note that not just the elements are the same, the number of atoms are also the same. Right? That's what it means to have a conservation of mass. And this is an example of a balanced chemical equation. Now we have enough theoretical foundation to balance our first chemical equation from scratch. We'll use for our first example the chemical reaction of burning methane. Now before we begin, I would like to stress that there are many ways to write balanced chemical equations, and what I'm about to show you is just one method of many that I find to be highly efficient. Make it a habit when you're writing a chemical equation to always start with a word equation. This would serve as a foundation from which you would build your chemical equation. When we burn methane, methane reacts with oxygen to form carbon dioxide and water. Next, we're going to replace the names of every term with their respective chemical formula. So methane would be CH4, oxygen would be O2, carbon dioxide would be CO2, and water would be H2O. Next, we're going to specify their state of matter, and recall this would be the state of matter as they exist during the chemical reaction. This is a highly exothermic combustion reaction, so the water that is produced would come out as steam rather than liquid water. Finally, before we start balancing the chemical equation, we need to count how many atoms of each element do we have originally. Once we have that, we are ready to balance our chemical reaction. The first step in balancing the chemical equation is to identify the element that is currently unbalanced. So we see that the number of carbon atoms are equal on both sides, so we can leave carbon alone. The number of hydrogen and oxygen atoms are not equal on both sides, and since we wrote hydrogen first, we can go about balancing hydrogen first. So the first thing we want to identify is the site with fewer number of atoms. In this case, for hydrogen, the site with the fewer number of atoms is the side of the products. So we can see that products has 2 hydrogen compared to the 4 hydrogen on the side of the reactants. What we're going to do next is to identify the product that the hydrogen came from. In this chemical reaction, hydrogen on the side of the product originated from H2O. The coefficient of H2O is originally 1. 1 H2O gives us 2 hydrogen atoms. What do you think we need to change the coefficient into so that now we have 4 hydrogen in order to match the side of the reactants? It would be 2 H2O. 2 H2O will give us 4 hydrogen atoms. Let's take a look. Right. So now we have successfully balanced our number of hydrogen atoms. Note that when we change the coefficient of H2O, we also change the number of hydrogen atoms because water contains hydrogen as well. So formerly we have 3, now we have 4. So our next move would be to balance the number of oxygen atoms. As before, we identify the site with fewer number of oxygen atoms, and in this case, it is the site of the reactants. So we identify the reactant where the oxygen atoms came from, and we see that it is the oxygen molecule, O2. So 1 O2 gives us 2 oxygen atoms. How many O2 would give us 4 oxygen atoms? You can probably guess that it is 2 O2. So now we have a total of 4 oxygen atoms on the side of the reactants. So it looks like our equation is already balanced. Let's double check. We have 1 carbon on the side of the reactants, 1 on the side of the products. We have 4 hydrogen on the side of the reactants and 4 on the side of the products. We have 4 oxygen on the side of the reactants and 4 on the side of the products. So there we have it, our very first chemical equation. If you managed to follow us this far, well done. If not, don't worry, we have another example. For the next example, we're going to use the chemical reaction of Haber process. Haber process is a chemical method of producing ammonia by reacting nitrogen gas with hydrogen gas. Our first step is to always start with a foundation of a word equation. So nitrogen plus hydrogen gives us ammonia. Next, we're going to substitute these names with their respective formula. Nitrogen is N2, hydrogen is H2, ammonia is NH3. It would help if you can memorize the formula for simple compounds such as ammonia. Next, we specify their state of matter as they exist during the reaction. For a Haber process, this takes a bit of background knowledge. So nitrogen, hydrogen, and ammonia all exist as gas during this chemical reaction. Next, we count the number of atoms of each element on both sides of the equation, and we see that none of the elements are balanced. Since we wrote nitrogen first, we can start balancing nitrogen first. So we first identify the side with the fewer number of atoms as before, and this would be on the side of the products. Next, we identify the product that nitrogen came from. In this example, it will be ammonia, NH3. So one NH3 gives us one nitrogen atom. So how many NH3 would give us two nitrogen atoms? We would need two NH3. Note that when we change the coefficient of NH3, the number of hydrogen atoms is also affected because NH3 is a compound containing both nitrogen and hydrogen. So the number of hydrogen atoms on the side of the products has increased from 3 to 6. So let's get on with balancing the number of hydrogen atoms. As before, we identify the side with the fewer number of atoms. That's the side of the reactants. Then we identify the reactants that the hydrogen atoms came from. This would be a hydrogen molecule, H2. So one H2 gives us 2 hydrogen atoms. How many H2 will give us 6 hydrogen atoms? We know that 2 times 3 gives us 6, so we'll need 3 H2. So let's double check to see if our equation is already balanced. On the side of the reactants, we have 2 nitrogen atoms. On the side of the products, we have 2 nitrogen atoms. So nitrogen is fine. On the side of the reactants, we have 6 hydrogen atoms. On the side of the products, we have 6 hydrogen atoms. So hydrogen is also balanced. So there we have it, our second balanced chemical equation. If you have found this video to be helpful, please like and subscribe. Thank you very much for watching.